Seriously though, when you consider that a fully loaded commercial jet can weigh hundreds of tons, the sheer impossibility of it soaring into the sky for hours just seems completely baffling, doesn't it? That massive machine effortlessly climbs into the atmosphere and hangs suspended for what seems like an eternity, all without any visible flapping wings or secret mechanisms doing the heavy lifting. What's actually happening underneath that aluminum skin is a magnificent combination of fundamental physics, precise airflow management, and incredibly smart, diligent engineering over many decades. Today, we are going to clearly dissect the core principles behind sustained flight, defining exactly what lift means, and clarifying some of the pervasive misconceptions that often confuse people about this amazing process. To truly grasp aviation, you must first focus entirely on one crucial concept, which acts as the very foundation for every single moment an aircraft is airborne: that upward force called lift. Essentially, lift is the magical invisible force generated by the wings that works directly against the constant pull of gravity, effectively suspending that enormous metal tube against all odds. During normal level cruising flight, the upward push generated by the wings must be perfectly matched in magnitude to the downward pull exerted by the total weight of the airplane itself. Whenever the pilot decides to gain altitude, the wings must deliberately produce a net upward force that exceeds the gravitational weight, pulling the entire machine down toward the Earth. Conversely, to initiate a controlled descent toward the landing strip, the system must slightly reduce that generated lift so that weight begins to take over the vertical movement. Therefore, if you want to understand any maneuver from a gentle turn to an emergency dive, it all fundamentally boils down to the creation, measurement, and precise manipulation of that essential lift force. The specially shaped cross-section of the wing, which engineers meticulously call an airfoil, is not accidental. It is a carefully calculated design optimized for moving through the atmosphere. If you were to slice through it, you would observe a gentle curve on top, a noticeably thicker leading edge up front, and a sleek tapering edge toward the trailing rear section. Now, while this cross-sectional shape certainly helps the process along, you must understand that simply having the right profile is actually insufficient on its own to generate the necessary power. The truly crucial element involves the dynamic and active way the wing surface successfully slices through the surrounding mass of air while the aircraft is aggressively moving forward. Once those powerful engines spool up, and the plane begins its rapid acceleration down the pavement, air immediately starts rushing over the top surface and simultaneously rushing beneath the lower surface of the wing structure. Crucially, the wing doesn't present itself perfectly flat to this oncoming stream. Instead, it meets the air at a slight upward tilt, which we scientifically term the angle of attack. It is precisely this intentional angle of attack that causes the underside of the wing to aggressively push that massive volume of air downwards and away as the wing passes through it. By actively redirecting the direction of a large quantity of moving air, the wing is fundamentally altering the air's path, which inherently means it is changing the air's momentum. This physical interaction is a perfect demonstration of Newton's famous third law of motion, stating clearly that for every action, there is an equal and opposite reaction force acting back upon the wing. That resulting, very real opposite reaction force pushing up against the wing is the magnificent, calculated phenomenon we define as aerodynamic lift. Perhaps you have previously encountered the very common explanation that suggests lift is solely caused by air speeding up over the curved top surface, consequently creating a region of lower static pressure up there. While that pressure differential is absolutely a real part of the equation, the simplified reasoning often used to justify it is frequently flawed or incomplete in its fundamental description. A common myth suggests that the air on top magically speeds up just to ensure it meets the air from the bottom simultaneously at the rear edge, which is simply not how fluid dynamics operate. Instead, the actual acceleration over the top occurs because the carefully designed shape and the established angle of attack force the entire airflow path to curve significantly downward, which requires increased speed. This accelerated, faster-moving air above the wing consequently generates that area of lower pressure, while the relatively slower-moving air being deflected underneath maintains a region of comparatively higher pressure. This resulting pressure imbalance between the top and bottom surfaces certainly contributes a significant portion of the total upward lift experienced by the airfoil. It's vital to remember that these two concepts, the downward push and the pressure difference, are not competing theories. They are merely two different interconnected viewpoints describing the exact same physical event. Moving beyond the wing's shape, The velocity at which the aircraft is traversing the atmosphere plays an absolutely non-negotiable and dominant role in this entire generating process. When the aircraft is moving too slowly, the wings simply do not pass through enough air molecules every second to deflect a sufficient volume downward to generate meaningful support. As the pilot increases the throttle and the airspeed rises, a much greater mass of air interacts with the lifting surfaces each second, causing that total upward lift force to grow exponentially. This fundamental relationship is the exact reason why every pilot must achieve a specific calculated ground speed before the wings can successfully generate enough lift to overcome inertia and depart the runway. Furthermore, this dependency on air density explains why aircraft flying at extremely high altitudes need to maintain a greater 30 true airspeed to compensate for the thinner, less substantial air molecules available. Beyond just the speed, the second key physical lever a pilot can manipulate to directly influence the amount of lift being produced is that all-important angle of attack. Generally, by slightly increasing that upward tilt of the wing relative to the oncoming flow, you can predictably increase the amount of lift being generated for better maneuverability. However, there is a critical limit to this strategy because pushing the angle too far causes the smooth airflow to violently detach and separate from the wing's upper surface. The moment that smooth laminar flow breaks down and becomes turbulent, the wing's ability to generate lift collapses very rapidly, causing a dangerous loss of control authority. Aviation professionals recognize this dangerous aerodynamic state where the wing stops performing correctly by giving it the specific name of an aerodynamic stall. It is crucial to understand that an aerodynamic stall does not automatically mean the aircraft is uncontrollably plummeting straight down into the ground, which is a common misunderstanding. Rather, a stall signifies the critical point where the wings, regardless of the engine power, simply cannot generate the required upward lift vector to successfully support the aircraft's current weight at that specific airspeed. Consequently, the ability to recognize the precursors to a stall and executing the correct recovery procedures remains one of the most fundamental and rigorously practiced skills in all of flight training programs. Shifting our focus from the wings, it's time to clearly address the role of those massive power plants mounted beneath or behind the cockpit, which are frequently misunderstood. One of the most persistent and fundamentally incorrect notions held by the public is the simple belief that the engines themselves are directly responsible for physically lifting the plane off the ground. That assumption could not be further from the aerodynamic truth. When we analyze the forces at play in sustained flight, the true function of the engines is to generate powerful forward thrust, a pushing force that propels the entire aircraft assembly relentlessly through the resisting atmosphere. This essential forward velocity created by the thrust is the prerequisite condition that allows the wings to begin interacting properly with the air to produce the desired lift. Even the most incredibly powerful jet engines operating at maximum output simply cannot haul a large airliner vertically into the air if the wings have zero airspeed across their surfaces to generate support. This direct dependency is perfectly illustrated by the silent flight of gliders, which rely purely on stored altitude, and conversely, by the immediate danger an airliner faces if it rapidly bleeds off airspeed. In summary, thrust is the necessary enabler of the flight process. It makes lift possible, but it absolutely cannot substitute for the aerodynamic function of the wing itself. Today's sophisticated aircraft are marvels of design, specifically engineered with multiple movable surfaces to allow pilots to manage and fine-tune the generated lift with incredible accuracy. During the critical phases of takeoff and landing, pilots deploy large movable sections on the trailing edge called flaps, which effectively increase the wing's surface area and its angle of attack for low-speed performance. Similarly, leading-edge slats extend forward to maintain smooth airflow attachment over the wing when the angle of attack is high, further delaying that dreaded stall condition. Other movable sections, like ailerons and elevators, allow the flight crew to dynamically shift the lift distribution across the span of the wing and maintain perfect three-axis stability. From the slightest curve to the largest flap, every single physical characteristic built into the wing profile serves the singular purpose of managing air movement and precisely controlling the resulting aerodynamic forces. Ultimately, the secret to flight is that the sophisticated wings are expertly designed to consistently redirect the surrounding atmosphere downward, which generates the necessary upward lift via momentum change and pressure differentials. Sustained flight is achieved moment by the pilot diligently managing the perfect synchronized harmony between forward speed, the precise angle of the wing, and the quality of the air flowing over it. Forget the mystical notions or the idea of some secret hidden natural loophole. This process is entirely mechanical and perfectly predictable according to established scientific principles. What you are witnessing is simply the relentless application of known physics, which has been meticulously refined through rigorous engineering testing and is validated with every takeoff worldwide. Consider the profound reality that an object weighing hundreds of tons can overcome gravity and ascend purely by harnessing the invisible power generated by moving the air molecules all around it. This incredible, reliable translation of fundamental science into real-world, heavy lifting capability solidifies aviation as arguably one of the most elegant and triumphant accomplishments in human engineering history.